So, guys, you're already here anyway. Please, let's give a round of applause to Professor Marcelle Machluf from the Technion Israel Institute of Technology and Yonatan Malca, the CEO of NanoGhost.
Thank you. Okay. So last, but I hope that not least, and I will do it in short as much as I can because I know that coffee is waiting. So NanoGhost is based on a technology that was developed in my lab. I'm from the Technion. I think we worked on it on 15 years until we decided to launch a company, but it's not only our decision, it's a decision from the investors and of course a long and hard negotiation with the Technion, but I think that today, after this case, they change all the way that they do it, and today, I think commercially, we see more and more technologies that coming very fast. The NanoGhost itself, the company, is based on a delivery system. It's a platform that the purpose is to deliver drug. We started as a company that wants to target cancer, and I will explain later on why. But later on, as we see in the company, we developed so many things, and we discovered so many things during the preclinical studies that we enlarged actually the portfolio of this company and actually become a platform that can deliver so many things. So the company itself was founded by myself. Yonatan Malca, as we will talk afterward, is the CEO that accompanied me since the negotiation with the Technion and later on building the company. We're already 4 years running. And Osnat Banakonash is the VP R&D, which could not make it today. So as I said, the technology is delivering drugs, but not only drugs, anything that we want directly to the tumor niche. And the problem is that usually when you do that, you have a system, you have particles, you have a delivery system, it's liposome, NLPs. You heard of so many particles that you need to touch a moiety that recognize the site of the tumor. And when you develop like ADCs, for instance, antibody, like we know about biological drugs, you need to direct it to a specific site of the tumor. Usually it's one type of tumor. And then sometimes when you find a drug that can be directed to one type of tumor, you try to make it work for other tumor. But the problem is the tumor changes and evade this system, and not all the patients are suitable for this therapy because not all the patients have the same marker, and cancer changes with time. So the idea in our technology is to take and build a particle that recognize all type, and I'm saying all type of tumor that resides in the body without doing much work. And the idea is to take a cell that resides in the bone marrow. The name is mesenchymal stem cells, as you see here. But I don't want a cell because the cells cannot do all that I want, and once it enters to the body control it, and I need something that is inanimate, something that I can control. We took the cell. Why these cells? Because these cells do recognize all tumor cells and do help the tumors to evade the immune system, and by that growing in our body. And the second feature is that this cell is a cell that can be harnessed or can be taken from all patients. I don't need the own patient cell. So we took the cell and we said, why the cell recognize the tumor? Probably whatever it has on its membrane. So why not to take only the membrane? And that's what we did. We actually emptied the cell from its content, and in biology it's called ghost, rendering the cell ghost, cannot divide, cannot breathe, cannot do anything. And then we took the membrane and downsized it to a small particle, which can be loaded with different drug, gene, DNA, RNA, whatever. The patent is huge, and I will, maybe Yonatan will mention it a bit later on. So we did so many studies, I will skip it just to show you a bit of data. The NanoGhost look like very spheric, very lipid-like wise, the same as, for instance, Moderna is using in COVID, but they are made from the membrane of this mesenchymal stem cells. and we can characterize them. And not only that, we made sure, as you see in here, this diagram, that actually they exhibited the same moieties, the same receptors, ligand that the cell has. We still keep them on this particle, which will designate their targeting to the cells. So for instance, this example, you see this NanoGhost in green. We put them on tumor cells, and immediately you can see how the cell uptake the NanoGhost, because they recognize them as the cells that comes to help them. But it's not. It's like a Trojan horse. And if it's not a tumor cell, then the NanoGhost will not be uptaken by these cells. So we wanted to go to the major problem in cancer, which is the blood-brain barrier and tumor cells. And we wanted to know if NanoGhost can go through this blood-brain barrier. And yes, it can bypass. Why it can bypass? Because the cell themselves can bypass the blood-brain barrier. And therefore, we assumed and we found out, of course, that these cells, that this NanoGhost can go. And if we initiate a tumor, the red that you see in the upper panel, in the brain, and we inject the NanoGhost IV, directly they will go to the tumor. Because they bypass the BBB, as I said, we started as a cancer targeting platform, but we said to ourselves, why not to target other disease? This is a mess. And what we can see here, that the brain is totally diseased with inflammatory, and we can see that the NanoGhost in red do arrive to the brain and cover all the brain. Not only that, I will skip this one. We tried also to see how we can modulate our system. And the beautiful with this system is that we can take the cell, engineer it to present whatever we want on its membrane, something that is missing or something that we want, and then make our NanoGhost. In this case, we render our NanoGhost to be NanoGhost PD-1. Now, clinicians do understand the PD-1, PD-L1 axis, which is a very important, just developing a drug, an antibody against that took $30 to $40 million, and not all the patient, of course, can respond to that. But we say, why not to do something simpler? So we took the NanoGhost, we expressed the PD-1 on their membrane, and give it to animals that had intracranial brain tumors, again injecting IV, and we saw that only the NanoGhost PD-1 without any drug reduced the tumor significantly and also extended the survival of this animal. And of course, in MS, I think that pictures or movies talks more than graphs. This is a diseased mice, paralyzed leg. We gave him 3 shots, and I'm not talking about only this mice, it's almost 100 mice that we did. We gave him 3 injections of empty NanoGhost, and what you see here is the mice is starting to walk and run, and the disease do not come back. And of course, it opens the door to Alzheimer's, other diseases that we can investigate. So the pipeline of the company is so diverse, but we had to focus, of course, and the focus is to deliver this NanoGhost together with RNA, which is the hot topic today, but also to direct the empty NanoGhost for different therapies, regardless of the drug inside. And of course, some of these projects are done in collaboration, and some are waiting for collaboration because they are too expensive. Now we are in preclinical studies, and we hope for 1.5 years to go to clinical studies. And the patent here is a very strong patent, covers the materials, covers the technology. It's approved in the US, Europe, and India. And of course, on top of that, we built several other patents, so the portfolio is just growing.
Just wanted to add regarding the business side that up to date we raised about $8.5 million in fundraising around A. In addition to that, we get 3 grants from the Israel Innovation Authority. So just I was asked to talk about our this is a session about tech transfer from the academia. So I just want to share with you our experience with this process in our case, is the Technion. So as you understand, the NanoGhost is a very wide platform, which is with many applications. So, but 4 years ago, when we founded the company, we didn't decide what would be the application that we start with. And in addition to that, Professor Machluf would continue to develop the NanoGhost in the Technion. So there is the potential for a new patent that we are afraid which could be out of the company. So we insisted that the license agreement with the Technion would cover everything. I mean, of course, the current patent, which is obvious, but also the future patent. Means the future patent, regardless if developed or registered by the company or by the Technion, this is what we did, and license agreement covers everything, which is very important. So my tip for those who want to get into negotiation with tech transfer, think about the future. Cover the future today. Don't wait. It's very important. So yeah, this is a win-win, and money and partnering. This is your answer.
You already answered the answer before I go ahead. That was just amazing solution, guys. Really, I mean, you saw the solution there in the mice, where the mice was paralyzed with the legs. I imagine it worked really well on university campuses for drunk students as well. You can give them a NanoGhost injection; they'll be walking again. No, but seriously, really quite an amazing solution. And without using drugs as well, quite phenomenal. What is the next stage? You said partners and investors. I assume I had a very quick question. How long did it take you to get this patent? Because patents take a long time to get approved. I don't want to take up too much time. I don't want to race to the coffee break. What's your time frame for this process?
The time frame, we submitted the patent 2009. It was already approved in 2016. Totally approved all the aims, very broad one. I was surprised. But on top of that, we built new patent that relies on the technology, so we can extend the lifespan of the patent. So 2017 was the initial patent. 2019, 2020 was the extension of the engineering of the NanoGhost. So that's
amazing. I mean, it's been in development since 2009, so that really speaks to how long this process has taken.
This is the medical area. You cannot take a technology like that and bring it so quickly. So the next step, of course, will take even longer, which is the clinical.
Absolutely, absolutely. Great stuff. So please put your hands together, Professor Machluf and Yonatan. Thank you so much.